We looked at static electricity or electrostatics, so now we're going to look at actual moving charges and Ohm's Law. So this is really the only other major equation you're going to see, different variants of it, and then one other one that we're going to see today. But other than that, the math in this is not difficult, it's a lot more conceptual. We'll start with looking at current, which is just the motion of charges through a material. So think of current as how many charges you have that are flowing, and the electrons are what move. It's the rate at which charges move through a wire. The symbol for current is a capital I. I know you've seen this twice before, and I'm sorry, but the symbol for current is a capital I. The unit for current is an amp, well, ampere. And the symbol for an amp is a capital A. Since current is the rate at which charges move through a wire, it's the number of coulombs per second. So that means that 1 ampere is equal to 1 coulomb per second. So charges need to be in coulombs and time needs to be in seconds. Equation for current, if it's not given to you, I equals delta Q over T. And this is on your formula sheet. So this is the change in charge. This is the time in seconds. And I is the current. Okay, so current, motion of charges through a material, in other words, how the electrons are moving. Next, we have the law of conservation of current, and that tells us essentially that the current is the same at all points in a current carrying wire. So just like energy can't be created or destroyed, charge can't be created or destroyed, current can't be created or destroyed within a wire. So that means that when you have, for example, a light bulb, the current going into a light bulb is the same amount of the current going out of the light bulb. You're not going to have electrons being destroyed or created inside the light bulb, so the total amount of current is not going to change. Okay, factors that are going to affect current would be the thickness of wire, material of wire, or the length of wire. So all of those things would determine, what kind of current you have. We're not going to worry too much about any of those things, but just know that those are what can change current. Okay, 2 quick examples. I'm really just going to do the first one. We have a 100-watt light bulb carrying a current of 0.83 amps. How much charge flows through the bulb in 1 minute? You know that current equals delta Q over T. So current times time will tell us how much charge is flowing. Really simple math. 0.83 amps times 1 minute would be 60 seconds equals delta Q. So this equals 49.8 coulombs. So delta Q is about equal to 50 coulombs. Okay, for the next one, I'm not going to go through the whole thing, but the answer should be, unless I made a mistake, 1 amp. Okay, now EMF. You're also going to see this being called potential difference, so you might see the words potential difference or voltage. I will probably use voltage more often than not. So EMF is the potential difference established by a device, such as a battery, that can actively separate charge. Think of the EMF as what gives a circuit the power it needs to be able to have charges moving. So in other words, something's not going to work without a battery or some kind of power source. So you'll hear me use the word voltage a lot more. It's the same thing as potential difference or EMF. The potential difference of a battery is equal to its EMF. So a 9-volt battery has an EMF of 9 volts. The symbol for EMF, and this is why you're going to find me using voltage so much, is a capital V, and the unit would be volts. The symbol for volts is also V. And this is just an intrinsic property of, say, a battery. And the last thing we want to look at for Ohm's law would be resistance. This is a measure of how hard it is for charges to go through a wire. The higher resistance means it's going to be harder to move charges. The symbol for resistance is a capital R, and the unit is an ohm, or ohms. The symbol for ohms is a capital Greek letter omega. So if you need practice drawing that, it kind of looks like a horseshoe. That was actually a bad one. Omega. 1 ohm is equal to 1 volt per amp. So that's what's inside an ohm. Okay, putting this all together in Ohm's law, it's going to describe the relationship between the potential difference, or remember, potential difference is the same as voltage, across a conductor and the current passing through it. Obviously, it's a conductor because conductors are the only materials through which electrons can move, so you can't really have a current through an insulator. The resistance is going to remain constant during use, and the equation for Ohm's law, V equals IR, Ver, where R is resistance, I is current, and V is voltage, or potential difference, or EMF. So again, you'll see all three of those used interchangeably. So very simple algebra when using Ohm's law. If something is ohmic, it means that Ohm's law applies to it. If something is non-ohmic, it means that Ohm's law does not apply to it. So something such as a battery or a capacitor, and capacitors we actually don't cover at all in this course. So let's just think of batteries. Batteries are not going to follow Ohm's law, so they are considered non-ohmic. You don't really need to worry about the fact that it's non-ohmic. Just know that we're really only using ohmic devices or materials. So it's ohmic if Ohm's law applies to it. Okay, power in a circuit, PIV. P equals IV. So this is power. I is current. V is voltage. Because of Ohm's law, which is V equals IR, power also equals I times IR, or I squared R. So you can also find power that way. You can make the substitution for I is V over R as well. So we know that I equals V over R, so power can also equal V squared over R. But this is the base one that I tend to go to. Okay, and last but not least, we have resistivity. This characterizes the electrical properties of materials. Good conductors are going to have low resistivity. The symbol for that is Greek letter rho, and that's a lowercase rho. It kind of looks like a cursive-ish P. The unit for resistivity is an ohm meter. And the equation, it's not necessarily for resistivity, it's more for how you figure out resistance. Resistance equals rho times the length of the wire over the area of the wire. So L is length, A is area, and this is resistivity, and that's your resistance. Okay, I'll do one example putting this all together, and then we'll do some practice tomorrow in class. Tells us that the glowing element in an incandescent light bulb is the filament, a long, thin piece of tungsten wire that is heated by the electric current through it. When connected to the 120 volt of an electric outlet, a 60-watt light bulb carries a current of 0.50 amps. What is the resistance in the filament of the lamp? So given this information, we want to use Ohm's Law. V equals IR, so V over I equals R. Your voltage, 120 volts, divided by your current, 0.5 amps, equals your resistance, 120 divided by 1/2, gives us 240 ohms for the resistance. Part B of this problem, at the operating temperature of a tungsten filament, the resistivity is approximately 5 times 10 to the negative 7th ohm meters. If the wire used to make the filament is 0.040 millimeters in diameter, how long must the filament be? So for this one, we want to have resistance equals rho L over A. So resistivity times the length divided by the area. We know from the first part of the problem that the resistance is 240 ohms. We are given the resistivity and we're given the diameter of the filament. So we need to figure out what the area of the filament would be. And for that, we're going to use, that area equals pi r squared. So if the diameter is 0.04 millimeters, the radius would be 0.02 millimeters. So the radius would equal 2 times 10 to the negative 5 meters, if I did that right. Okay, so looking for the length of the filament, rearranging this, we get that L equals resistance times area over resistivity. So this will equal our answer from part A, 240 ohms, times the area, so this would be pi times 2 times 10 to the negative 5th meters squared over 5 times 10 to the negative 7th ohm meters. Ohms cancel, one of those meters goes away, we're left with units of meters. And this is going to come out to 0.60, keeps on going, meters for L.